I leave the stage to Stelios. Thanks.
Okay, Valentina, thank you very much for your kind introduction. It's a real pleasure to meet you all through this virtual platform. And I hope that all you are keeping yourself healthy and be well. So let me turn off my camera first and share my screen. Please let me know if you can see my screen.
Yes, I can.
Okay. So before I begin this presentation, I would like to thank SECED young members for the invitation to talk about my research work, and of course all the attendees who joined today's seminar. I hope by the end of this session there will be some useful takeaways for all of you. So for those who don't know me, my name is Stelios Minas. I'm an earthquake engineer, and I'm specializing in seismic vulnerability of reinforced concrete buildings. For the last bit more than 1 year, I'm working as a risk consultant for AIR worldwide, and I'm based in Singapore. But today I'm mainly going to talk about my research work that I carried out during my engineering doctorate. Specifically, I'm going to talk about the advancements in the seismic risk assessment of mid-rise reinforced concrete buildings, which is also the title of today's presentation. In particular, we are going to look together more closely into existing catastrophe and seismic risk framework, and we will seek for possible ways, approaches, or models in order to improve it. And how we are going to do that? Well, let's have a look. So let me start a bit with the agenda of today's presentation. First, we will talk about introduction and background, where I will try to provide some research motivation and also the aims and objectives behind this research project. And then we will also introduce the basic steps of catastrophe modeling. Next, we are going to look into the probabilistic regional seismic loss assessment and different modeling options. So we will show hazard and vulnerability options that are currently available in the literature. Some of them are used in catastrophe models, some others are the state of the art and probably will be incorporated in future catastrophe models. I will also take the chance to talk about a little bit about tools that I developed or co-developed during my engineering doctorate. And then we will introduce a case study where we are going to see the seismic risk model for Avellino. We'll discuss some of the details of the studied seismic risk model about the exposure assumptions, the hazard and vulnerability module. And finally, we will look into the sensitivity of seismic loss estimation to modeling options. Now, a little bit about the research motivation. Major earthquakes are responsible for an annual death toll of about more than 60,000 people, and also have economic losses which can significantly impact the world's economy. In particular, the densely populated urban centers are exposed to high seismic risk. Despite the major advancements in seismic design standards, building codes, and practices, recent earthquakes in the Mediterranean, for example, in Italy, Turkey, and Greece, have resulted in extensive damage to the built environment and also numerous human losses. As we all know, reinforced concrete buildings constitute a significant part of the Mediterranean building stock. And those recent events reminded us the high vulnerability of that building type, and also highlighted the need for more reliable models to estimate the expected losses and also quantify the possible risks. So how we are going to tackle this problem? By implementing loss models, the so-called catastrophe models, in order to perform seismic risk analysis. The idea of such models is to estimate the losses for a set of a given location, building portfolios for specified return periods. This is done by integrating the hazard, the vulnerability of the built environment, and the exposed value at the area of interest. Of course, there are several sources of uncertainty which are identified within all these aspects and required to be assessed in probabilistic terms, which, as you can imagine, it adds an extra layer of complexity. Now, at the bottom of this slide, So at the bottom of this slide, you can see the typical catastrophe modeling framework as developed by AIR worldwide, which of course is very similar to the framework that is used for other catastrophe vendors or researchers. So this framework is divided into three main modules. We have the hazard, the engineering, or sometimes referred to as vulnerability module, and finally we have the financial module. Now let's have a look at each one of these modules as well as the underlying components. So here in this slide you can see exactly the same framework as showed in the previous one, But in this example, we are going to mainly talk specifically about earthquake catastrophe models, starting with the hazard. So the hazard module is divided into two subcomponents. We have the event generation, and here we'll try to answer questions regarding the location, the intensity, and the frequency of the events. So for the case of earthquake model, the historical events are recorded in one area and combined with the local seismic sources in order to generate what we call stochastic catalog of events. Next, the second subcomponent of this module is the intensity calculation, where here we try to answer questions like what is the intensity of each event at each location and how will local conditions affect this intensity. This is done by utilizing a number of ground motion predicting equations, which are also known as attenuation relationships, which, for those who don't know, are empirical relationships that describe the intensity levels as seismic waves propagate away from the seismic source. This empirical relationship take into consideration the soil conditions, the fault characteristics, the depth, and the distance from the location of interest in order to compute the estimated intensity. Now, the next component, the next module is the vulnerability module or engineering module, as we mentioned earlier. In this module, the overall damage of the exposed properties is estimated based on the hazard intensity as calculated from the previous module, and also the exposure data that are associated with the location of interest. The output of this module are the fragility curves. Fragility curves, for those who don't know, are statistically representing the probability of exceeding a certain damage state or performance level as a function of the ground motion intensity. An example of fragility curves can be seen on the top right corner of this slide, but later on in this presentation, we are going to give a bit more details. Finally, the damage that we obtain from the vulnerability module is translated into economic losses by taking into consideration the policy conditions for the properties that we are modeling within the financial loss module. Now that we have given the background and introduced the basic concept of seismic risk models, we are going to look into different ways to enhance such models. So in the past, there are several researchers that have attempted to explore, for example, the effect of spatial correlation of ground motions or the variability of the exposure model within the seismic loss framework. However, there is very limited research that has been done on the, for example, the effect of intensity measure choice or analysis types and so on. So in this talk, we are going to investigate how the different input modeling options influence the estimation of losses. So the main objective is to systematically assess alternative methods for representing the seismic hazard and vulnerability and try to prioritize the areas where a catastrophe risk framework could potentially improve in the future. Now, talking about the seismic hazard, we looked into the ground motion intensity characterization through selection of different types of intensity measures and also ground motion correlation models. And also, we assessed the impact of spatial scale. With regard to seismic vulnerability, we tested the effect of structural analysis methods by comparing simplified nonlinear static procedures versus advanced nonlinear dynamic analysis. And finally, we tested a newly developed fragility derivation approach against the standard approaches that are used in catastrophe models. Now, let's move on to the next section, which is the probabilistic regional seismic loss assessment, considering the different modeling options. So understanding the impact of the different components in the loss estimates will contribute towards the development of a more robust seismic risk framework. And this will also serve as a guide to prioritize the potential improvements for future catastrophe models. As we showed in the previous part, in the previous slides, here we are going to investigate the effect of 5 modeling options. So we have modeling option 1, which is about the intensity measure types. The second one is about correlation model, the spatial scale, and then we have fragility related modeling options. For example, the analysis method used and probabilistic seismic response analysis method, which we are going to explain later on what exactly is. So it is noteworthy to mention that some of these options tested here were developed as a part of this study. Starting with the modeling option 1, which is about the selection of intensity measure types. But let me remind you first what an intensity measure is. So intensity measures are scalar or vector-valued ground motion parameters that are considered to be representative of the earthquake damage potential with respect to a specific structure. So for simplicity, in this project, we divide the intensity measures into two main categories. So we start with the standard intensity measures, like the ones we all know, for example, peak ground acceleration or spectral acceleration at different periods. And in general, standard intensity measures are widely used in design codes and cat risk models. However, there are several studies that have showed that they are poor predictors of structural response of buildings that are mid or high rise, and they must be used with caution. On the other hand, we have the advanced intensity measures, such as the average spectral acceleration over a range of periods. And the advantage of this is that they can account for an enhanced range of periods, which can better correlate to the building response for higher mode effects and elongated periods. The superiority of advanced intensity measures is also evident as they also perform better than standard ones over different performance metrics, which are known as intensity measure selection criteria. For example, efficiency, sufficiency, hazard computability, and so on. So for this modeling option, we selected one intensity measure to represent each category, as you can see in the table at the bottom of this slide. So we chose SAT1 as the standard intensity measure, which is also typically used in many catastrophe models. And as an advanced intensity measure, we chose INP, which is a spectral shape-based intensity measure proposed by Bohorquez and Yervolino. Now, if you want more details on the choice of the aforementioned intensity measures, you can always refer to the research study, which is shown on the bottom, where we assessed the performance of a number of the different intensity measures, both advanced and standards, under 5 different intensity measures selection criteria. Now, let's have a look on the modeling option 2, which is about the correlation models. So a correlation model provides information on the correlation between ground motion intensities at different sites during a single event. At this point, I promise I'm not going to go through all those scary and long formulas, but rather I will give you a brief description of the 3 chosen options. And starting with the first option, which is the most sophisticated one, is the full block cross correlation model, or simply referred to FBCC, which combine both spectral and spatial correlation model, providing the cross correlation between the residuals of 2 different ground motion intensity measures at 2 different sites. This option is particularly important, for instance, when assessing the risk of a portfolio of buildings with different fundamental periods. The second option is a simple spatial correlation model, which we will simply call it SSCM. And finally, we have the third option, which is not to use any correlation model, and we will simply call it NC model. The next modeling option is the selection of spatial resolution of the exposure for a considered portfolio of buildings. This is a rather straightforward case, as we only have 2 options: the low resolution, which is 500 by 500 meters squared, and is the resolution commonly found in many existing catastrophe models. On the other hand, we have the high resolution, which is 250 by 250 meters squared, which provides, of course, a finer representation of buildings' exposure. Now, one of the most crucial modeling options that we tested here is the choice of analysis methods. In short, here we tested 2 broad analysis method categories, namely the standard and advanced methods. On one hand, we have the nonlinear static procedures, such as N2 method or FRACAS. These are capacity spectrum methods which rely on simplified pushover models in order to compute the seismic response of the structure in question. These approaches are very simple and rapid, which makes them more popular for applications like CAT modeling, where a large variety of construction need to be analyzed. However, one of the main limitations of those methods is that they cannot capture certain response behavior, such as higher mode effects or torsional phenomena. On the other hand, we have the advanced nonlinear dynamic analysis, such as nonlinear time history analysis, which I'm pretty sure that most of you are very familiar with. So these methods require to model a building in great level of detail and produce more reliable results. Of course, this comes at a significant computational cost, making such approaches a bit less favorable for portfolio applications. Now, let me share a few more information about FRACAS, which is the standard nonlinear static procedure that we used here. and was also developed and enhanced as a part of this research project. So FRACAS, which stands for Fragility Through Capacity Spectrum Assessment, is an automated tool in order to compute the analytical fragility curves, and is based on the nonlinear static procedure developed by Rosetto and El Nasai. FRACAS is using inelastic spectra from ground motion records and can account for the record-to-record variability in the evaluation of performance of a single or a population of buildings. This is an important improvement in comparison to other simplified methods, which only use smooth response spectra found in seismic codes. FRACAS is recommended by the GEM guidelines for analytical vulnerability assessment of low and mid-rise buildings, and it's freely available through the Epicenter website by accessing the link that I'm providing over here. Now, here is a visual depiction of FRACAS main steps, but due to the purpose of this talk and the time constraints, I'm not going to go into more details. However, for those who are interested to find out more, I have provided a reference study at the bottom of this slide, which discusses in detail all the steps and the background of this approach. Now, before looking at the different modeling options for fragility assessment, let's do a quick refresher of what fragility function is. Fragility function, or sometimes called fragility curves. A set of fragility curves statistically represent the damage as a function of ground motion intensity. So as you can see in the graph below, x-axis corresponds to ground motion intensity expressed in terms of intensity measures, or IMs. Some of the typical intensity measures that we see are PGA, SA, and others. While on the y-axis, we have the probability of reaching or exceeding a certain damage state given an intensity measure. So we have three continuous thick lines which correspond to the three different damage states based on their color. So for example, this damage stage could be slight damage, moderate damage, and complete damage, but this also depends on the choice of the damage scale. You can also see two dust lines for each of the damage states, which represent the 5 and 95% confidence bands. So now that we have seen how fragility functions look, let's have an idea about what are the simple steps to construct such fragility functions. So first of all, let me tell you that there are different types of fragility curves. We have the empirical, analytical, expert judgment fragility curves, and we also have a hybrid combination of two or more types of fragility curves. But in this case, we will only focus on the analytical fragility functions. So having said that, the first step is that we need to create a building model in a finite element software, such as ETABS, OpenSeas, or Seismostruct. So once we have a detailed model, the next step is to perform the analysis by subjecting the building to multiple seismic excitations of increasing intensities, and to compute the seismic response of the building for these associated seismic excitations. As we showed in the previous slide, this can be done either by using simplified or advanced analysis methods. So for the seismic input, we record the ground motion intensity in terms of intensity measure and plot it against the building's response, which is expressed in terms of what we call engineering demand parameters. Just to give it an example, a commonly used engineering demand parameter can be the top level displacement or the top drift, or it can also be the maximum interstory drift and others. Now, if we plot a graph, on one graph, 1 point for each seismic input and the associated response, then we will end up with a collection of points which form a cloud of data, as shown in this small graph at the bottom of this slide. So the last step is to carry out what we call probabilistic seismic response analysis, where we implement a statistical model to fit our data. And based on the model parameters, mean and standard deviation, we can then construct the fragility functions as shown here. Of course, this is a very simplified way to describe the derivation process of fragility curves, but it gives you an idea for what we need to show later on. So, having discussed the concept of fragility, we can now look at the modeling options for case number 5. This is associated with the choice of probabilistic seismic response analysis. And as before, in this test, we are also going to compare a standard and advanced method. The method that we chose to represent the standard methods is cloud analysis. This is a very simple statistical regression model in order to fit the mean EDP given IM relationship and calculate the associated variance. The advantage of this approach is that it's simple and fast. However, it is relying on some simplifying assumptions. For example, it is using a fixed mathematical model that assumes that the expression of the probability distribution of EDP given IM is constant, which is not always a valid assumption. On the other hand, we have the advanced method BEA, which stands for Bayesian Emulation Analysis, which was also developed as part of this research project in order to overcome some of the limitations of the standard model that we showed above. BEA is a Bayesian emulation-based approach in order to compute the mean estimates and the associated variance for the conditional distribution of EDP given IM relationship. Now, the advanced statistical model utilized for this method allows for a fitting flexibility and provides better uncertainty characterization due to the Bayesian framework utilized. Another advantage is that this approach results in a significant reduction of computational time, as a smaller number of analyses is required to train our statistical model. Of course, the limitation of this approach is that it's quite complex to build. Now, that was the theoretical part, but let's have a look at a more practical example to better understand how these two different methods work. So the superiority of the advanced model can be seen when attempting to capture the true IM and EDP relationship, which is shown in black lines in the two graphs on the left, while the blue lines show the model's means estimate, as you can see here and here. The better fitting of the advanced model, which is apparent from these two graphs, is also translated to better capturing the true fragility as shown on the right-hand side graphs. So again, the black lines correspond to the true fragility, while the thick yellow and green lines correspond to the modeled fragility. And in the case of the advanced model, we can see that the two sets of lines are almost identical, while in the case of the simplified model, there are some discrepancies. Now, for more details about the BEA method, again, I have provided a study at the bottom of this slide where we explain all the steps and all the details on how to build and how to run this kind of method. Okay, so we have already discussed about the different modeling options, and now we can move on the next section where we are going to present a simple but realistic example for assessing the sensitivity of probabilistic regional seismic losses to the different modeling options. So our case study here is going to be the city of Avellino, which is located in southern Italy. And the first question that comes to mind is why we chose Avellino. So Avellino municipality is the capital of the province of Avellino in the Campania region in southern Italy, and is well known about the high seismicity hazard. More specifically, two major events have occurred in that area in the last 90 years. So in the 1930, there was a magnitude 6.7 event, which caused more than 1,400 casualties, while a more recent event in 1980, moment magnitude 6.89, which resulted a total of more than 2,500 casualties. And here you can see on the right-hand side pictures from the damages from those two events. Now, another reason for choosing this location is because according to the Italian census data and also some recent field studies, the building exposure in that city mainly consists of mid-rise reinforced concrete building population, which is about 80% of the total building inventory. And because this study is about mid-rise reinforced concrete buildings, this was ideal example to test our models. Here, we are going to look more closely into the exposure models, the exposure model that we used, and also the associated assumptions. For this case study, we assume that the entire building stock consists of mid-rise reinforced concrete buildings. As we explained in the previous slide, this is a perfectly valid assumption, so we can ignore all other building types. The buildings are spatially distributed according to their exact location based on the information that we found from OpenStreetMaps. Now, on the map here on the top, shows the location of more than 3,300 exposures divided into 3 vulnerability classes based on the year of construction. So here we have the pre-code buildings, which account for 32% of the exposure. Then we have the low-code buildings, which is 60%, and finally we have the spatial code buildings, which the 8% of the total exposure. So the different colors correspond to different vulnerability classes. The red color corresponds to pre-code buildings, the green code to low-code, the green color, sorry, to low-code, and the blue color to spatial code. As you can see in this map, and like in most Mediterranean cities, the majority of older buildings is concentrated at the historical center and is surrounded by newer buildings, in this case, the low-code buildings. And the majority of new build structures are usually found at the outskirts of the city, far away from the center. About the hazard model, and particularly about the intensity calculation, we used the 10,000 year stochastic event catalog, which was provided by AIR worldwide. This catalog includes more than 25,000 events and was developed for the entire region using GMPs for Italy and the Mediterranean, and also takes into consideration ground motion conditions, solar amplification effects, and so on. As a result, we have the footprints of 4 different intensity measures, namely the PGA and the SA at 3 different periods, 0.3, 1 second, and 2 seconds. At this point, it is worth noting that these 3 spectral acceleration for different periods allow us to calculate the values of an advanced intensity measure, such as INP, that we mentioned earlier, which is based on the geometric mean of spectral acceleration at different periods. Now, for the vulnerability model, we used 3 building models representing the typical Italian buildings of the 1940s, 1970s, and also a modern design. As we mentioned before, these are all mid-rise reinforced concrete buildings, moment-resisting frame, and they share exactly the same geometry, but correspond to distinct vulnerability classes, as we mentioned earlier. So the buildings are those buildings are designed according to those codes and are subjected to a large number of unscaled earthquakes, and their seismic response is calculated, and the fragility functions were derived based on the modeling options that we discussed in the previous part of this presentation. Please note that for the fragility derivation, we assume that the natural period of all 3 buildings is equal to 1 second. This is a standard representative period that is used for mid-rise buildings in catastrophe models. The results of this process is a total of 24 sets of fragility curves based on the 3 different vulnerability classes, 2 different analysis methods, and 2 IM types and 2 PSRA methods. And here are the fragility curves that are developed for this study. Each set of curves provide the mean and associated confidence bands for 3 damage states, which in this case is low to moderate, heavy, and collapse. And as you can see here, the first 2 columns correspond to standard fracas analysis. One column for each intensity measure. So here we have SA and here we have the INP. Each row represents the different vulnerability classes. So we have pre-code, low-code, and spatial code. Now, the fragility curves are converted to 24 equivalent vulnerability curves by using the simple damage to loss model developed for the Italian region by Di Pasquale and Goretti. And it's also used to help us calculate the losses in the latest part of this presentation. And here is the set of the vulnerability curves that we developed here. Now, in this section, we are going to evaluate the seismic losses by using the probabilistic event-based approach. So here is the step-by-step procedure that we followed. The first step is to use the AIR stochastic catalog of events that we mentioned a few slides earlier. Next, we are going to evaluate the aggregated losses for each simulated earthquake event. And from the resultant set of portfolio losses, we will build the exceedance probability curves, or simply called EP curves. The EP curves describe the probability that various levels of loss expressed in euros, dollars, or other currencies will be exceeded over a specific time frame, usually 1 year. To better understand the impact of of different input assumptions in risk analysis, we are going to perform a comparison of the estimated losses in terms of exceedance probability curves for different modeling options. Okay, this table simply shows, reminds us again the 5 different options. And here we have the standard and the advanced approach for each of the 5 modeling options. I'm not going to repeat this. We have already talked about it a few times. And in this first example, we will assess the modeling options 1 and 5, which means that we are going to compare the estimated losses when using different intensity measures and PSRA methods. For this reason, the other input options such as analysis type and correlation model will be kept constant among all the compared cases. So we created 2 versions of EP curves. We have the left panel where EP curves are expressed in terms of loss per unit area, while on the right panel we can see the loss is normalized by the best available model, which is also going to be our benchmark model for this comparison, but also on the comparison that we'll see in the following slides. In a second, I will explain exactly what is the benchmark model that we used here. Now, let me explain what are the different colors of the curves that we see here. So the red color, we have a dust line and continuous line. The red color corresponds to the standard intensity measure SA, while the blue color corresponds to the advanced INP intensity measure. And the continuous lines correspond to the advanced BEA method, while the dust lines correspond to the standard cloud method. Of course, there is a black thick line, which is associated with the benchmark model and combines the advanced options, and in this case, it's going to be INP and BEA. The other two, the other options are fixed for all the compared cases. Now, let's have a look on the observations. There's a significant difference in the loss estimation for the different types of intensity measures. In general, the advanced intensity measures can capture more information and can significantly reduce the effect of the ground motion characteristics to the predicted structural response and consequent loss. On the other hand, the PSRA methods appear to have a smaller influence. So, for example, when comparing the 2 red lines, which use a different PSRA model, you can see that the difference is almost negligible. However, the PSRA methods have a highest impact when combined with an advanced intensity measure, as they can take advantage of the additional information provided by an advanced intensity measure such as INP. Now, in this example, we will investigate the effect of modeling option 2. So to this aim, we are going to compare the estimated losses when using different correlation models. But of course, we are keeping, again, the same intensity type and analysis method. This is something that has been done in the past. So for this example, we have the 3 correlation models. The first one is the black line, which is our FBCC model, which is our sophisticated benchmark model. Then we have the blue line, which is the simple spatial correlation model, and the red line corresponds to the case where no correlation model is used. The general observation here is that the inclusion of correlation models increases the losses, and this observation comes in agreement with the other previous studies performed in this field. So as expected, our benchmark model, which is the FBCC, produces the highest level of losses. On the other hand, we can see that the SSC, which is the simple spatial correlation model, the losses are lower compared to FBCC, but they are closely matching at higher loss levels, and this can be seen at the normalized exceedance probability curves at the lower part of this graph. Finally, the result of NC model, of no correlation model, deviates substantially, as we can see here, from the other 2 models, and therefore is not recommended to be used. The third example, we are going to assess the impact of the spatial scale. Therefore, we will fix the intensity measure and analysis method and correlation model, similarly to what we did before. For this test, we only compared the 2 spatial scale resolution, the high resolution, which is plotted in black, And we also have the low resolution, which is plotted in blue. In general, the higher spatial resolution ensures that a more refined intensity representation we have a more refined intensity representation of footprints, and as a result, we have a more realistic representation of losses. This comparison confirms that the lower resolution option cannot really replicate very well the high resolution results and produce a shift of losses to significant higher levels. The observations that were drawn from this test are consistent even when we are using different modeling combinations. So we have fixed certain combinations here, but even if we choose to change those, the observations are very, very similar. In this final example, we investigate the effect of modeling option 4, which is about the choice of analysis methods. The simplified method FRACAS is shown in magenta line and is compared against the advanced model nonlinear dynamic analysis, which is shown on the black line and is also our benchmark model. This test highlights that the choice of structural analysis approach is the most important in the loss calculation. And specifically, FRACAS analysis results are significantly underestimating the loss, especially at lower return periods. This can be explained by the fact that simplified analysis approach cannot really capture some damage mechanisms that have a significant impact at lower level of losses. This can also be seen here. So, however, at this point, we should note that the FRACAS is still one of the most advanced nonlinear static procedures and outperforms the most commonly used CSM approaches that we find in catastrophe models. So to wrap up, for this research work, we performed a systematic probabilistic regional seismic loss assessment for reinforced concrete buildings, where we tested different types of hazard and vulnerability modeling options, including some of the latest advancements that are found in this field. The city of Avellino in South Italy was used as a case study. So we developed new methods and tools and put them into test against some of the most commonly used practices in existing CAT risk framework. The outcomes of this study can act as a guide to highlight areas where future catastrophe models or risk frameworks could be improved. Based on the results of this work, we can conclude that the analysis methods have the most significant impact in loss estimation. Advanced analysis more realistically capture failure mechanisms and predicts losses more accurately. In addition, the selection of IAM type is also of high importance. The advanced intensity measures are able to capture more information, and in a way, they can significantly reduce the effect of the ground motion characteristics to the predicted structural response and consequent loss. Finally, the other tested choices, such as the choice of correlation models, fragility derivation methods, and spatial scale resolution, do have an impact on the seismic loss estimation, but the impact is not as significant as in the other modeling options discussed above. Before we reach the end, I would like to acknowledge my academic supervisors, Professors Tiziana Rosetto, Carmine Galasso, and Richard Chandler, and my industrial advisors, Dr. Luis Soja and Dr. Tristan Lloyd, for their help and the significant contribution for every single part of this work. And finally, I would like to acknowledge my research sponsors, EPSRC and AR Worldwide, for funding this research work through the Urban Sustainability and Resilience Program at UCL. Last, I would also like to thank Epicenter Research Group for providing technical support at many different stages of these projects. And with this list of publication and references, I will conclude today's talk. Thank you very much.
Thank you very much, Stelios, for the very interesting presentation. And I think it's now time for any question that you might have.
Yeah, sure.
Any question? I have a question.
Yes, please.
In your sensitivity analysis, which parameters did you consider, and which one of them are the highest effect in your results?
Okay, so as we mentioned, there are 5 different areas that we looked at, the 5 different modeling options. So we talked about the analysis option, we talked about the fragility derivation methods, we talked about the type of intensity measures, we talked about the correlation models, and we also talked about the spatial scale. So the biggest impact in the loss estimation was related to the analysis options that we are using. So, for example, when you're looking into a simplified analysis method, as we mentioned, there are certain advantages by going with this option. However, this also comes with certain types of limitations. Simplified methods can only account for a specific number of failure mechanisms. It cannot really capture the different types of behaviors that a complex building can experience. For this case, there is a lot of damage potential that can be ignored when using a simplified method. So this can explain the reason why the impact of the choice of analysis method has the highest contribution. Of course, all methods, all different modeling options can have an impact, but in terms of if we are trying to account what is the highest impact, it will be definitely be associated with the choice of the analysis type.
Okay. Okay. But your simplified method was based on certain type of parameters, geometry or material properties. I'm just interested in knowing which one of the 2 classes, for example, was more impactful in your results. I know that you mentioned that the simplified methods were underestimating the losses, determination of the losses, but I just wanted to know between these 2 big families of geometric parameters or material parameters, which one of the 2 was more impactful, if you could say.
Okay, so we used exactly the same building models for both cases. So what we can possibly say is about which vulnerability class was more affected by the choice of analysis type. So in that case, it will definitely be a pre-code building. And this is because a pre-code building is not seismically designed, so it can experience different types of failure mechanisms. While when you have a very well designed spatial code building according to modern codes, and in this example we designed buildings for the Italian region, which has very advanced seismic codes. So the performance of those buildings was very, very well captured, even from simplified methods. But as we showed in this example, because in our exposure, only 8% of the inventory corresponded to spatial code buildings, even it was the area where a simplified method could do quite well, but it was such a small proportion of the overall exposure that showed the limitation of that method, if I may say.
Okay. There is a question from Sarah.
Okay.
Thank you for the presentation. Very interesting. Where do you see your next steps going forward with this research?
Okay, so the next steps. So what we presented here is a part of a journal publication that we are currently drafting, and we hope to. So we are the last part of drafts, and hopefully we will submit it very soon. There are a lot of areas that could be potentially improved, and one of these areas is so. This was a relatively simple seismic risk framework that I followed, because as you can imagine, this is like a very long process, and it requires a high level of detail at its stage. But it's practically impossible for one person to develop, the hazard model, the vulnerability model, and so on. And one of the most crucial parts of this work is to evaluate your final results. So in our case, what we did is we just chose the best available model. So we used all the advanced options and we said, okay, this is our target. And we tried with the simplified standard approaches to see how close we get to those advanced like benchmark model. However, if we had the option, it would be good to test these modeling choices against real losses. So from a real loss event, from what we see in practice, and see whether our numbers are close to what happens in reality.
Thanks. Any other question? Doesn't seem like any other question is coming. Thank you. Good luck with it. I think no more questions are arising. So in a normal situation, you would get a big round of applause, but thank you very much for the interesting presentation. And hope you all have a nice rest of the evening. And thanks a lot, Stelios, again, for joining us today.
Thank you very much, Valentina, for the invitation. It was a really nice experience, and I hope that there were some interesting takeaways for people that attended this.
Definitely.
And I hope that everyone is well and keeping themselves safe during this difficult situation for all of us.
Thanks a lot.
Thank you.
Bye.
Bye-bye.